Hi guys, this is Miss McKahan. Sorry I'm sick today. I still wanted to make sure that you guys could move on even though I'm not there. First of all, I want to remind you that if your shoebox projects are due next class on Tuesday, most of you showed me your solutions, but if you wanted me to look at your solutions, please just type them up and email them to me, and I'll try to give you some feedback over the weekend. But if not, don't worry about it, and then we'll just grade them on Tuesday. Also on Tuesday, we're having that mini assessment. So remember, that's going to cover the true-false over continuous and differentiable, and the multiple choice that's talking about continuity, and then the related rates problem. So be prepared to take that on Tuesday still. All right, as far as your homework questions, I'll have to answer those on Tuesday when I come back. Hopefully, maybe I'll be back on Friday. Maybe you can come into lab if you have some questions. All right, but otherwise, let's get started with section 3.3. There should be handouts for you, so you can fill them in as you listen to this video, or you can do them on your own and then just listen to this video to clarify anything. All right, so in section 3.3, we're really talking about the idea of increasing and decreasing. I think we know intuitively what it means. It means, increasing the functions going up or down. But technically, if we're talking about the x values, if I'm going from left to right, so that means that my second x value is larger than my first x value, then we know that the function is increasing when the y value gets bigger than the first original y value. So like you can see here in the graph, if I go from left to right in my x's and trace this, then my y values get larger and larger. And then just the opposite for decreasing. As I go left to right on my x values, my function values decrease, so they get smaller and smaller. So going left to right, my y values get smaller and smaller. And then the idea of constant, we already talked about that, the y values stay the same. So we're going to use the first derivative to help us determine increasing and decreasing on a graph without having to look at the graph. So here's how we're going to do that. If we look at the first derivative, remember that's the slope. That's the slope of our function. So if our slope of our function is greater than 0, if it's positive, then we know that it is going to be increasing. Okay, think about what a positive line looks like and how that would look on an increasing graph. And then here, if our derivative, our slope is negative, less than 0, then that's going to be decreasing. And then, of course, we've already talked about when the derivative is 0, that means it's constant. And we talked about how those are the relative min and maxes. Now, a function can be strictly monotonic. So just a little vocab for you there. That just means it's always increasing or always decreasing. So right now, think of a function that's always increasing, like a cubic function. All right, so let's look at an example here. We're going to try to determine where this function is increasing or decreasing. So first of all, we're going to find our critical numbers, and that's whenever our derivative is equal to 0 or does not exist. So here we've got our derivative. We're going to set it equal to 0. Solve it, and we get x equals positive and negative square root of 6 over 6. All right, I'm going to use this approximation later. You'll see why. All right, so let's chart our findings here. We've got our intervals and our critical points. So here I've got my first critical point, negative square root of 6 over 6, and here I've got my second critical point, positive square root of 6 over 6. And then my intervals are just going to be on either side of those critical points and in between. All right, so here's where we need our approximation. In this interval where it's less than negative square root of 6 over 6, I'm going to plug in a number that's less than negative 0.408, so maybe like negative 0.5. So plug that in to your derivative. Make sure you're plugging it in here, not in here. So if we plug negative 0.5 in here, we'll get a positive value, and I don't care what the actual value is, I just want to keep track of whether it's positive or negative. We know that at the critical point it's going to be 0. The derivative value is 0. And now in between, we're picking a number in between negative 0.408 and positive 0.48, so that would be like 0 would be a good number for that. We'll get a negative number. And then for our second critical point, we know it's 0. And then we plug in a number that's greater than 0.408, and then we get a positive number. So here we've tracked all of our derivative values. There we go. All of our derivative values. And now we can determine where it's increasing and decreasing. So wherever our derivative is positive, that's where it's going to be increasing. Right here and here. And here is where it's going to be decreasing. So you just write up the intervals. Remember, just use the open parentheses for intervals. The first derivative test is going to tell us about the critical points. Okay, it helps us classify whether the critical points are either a relative min, relative max, or neither. So what's important here, make sure you are looking at this first condition. C is a critical number of the function. The function has to be continuous. And note here, it has to be differentiable on the interval except possibly at C, because remember we could have gotten that critical point when the function's derivative did not exist there, so that's possible too. So keep in mind that. So here are our options. If we have our derivative that changes from negative to positive at C, then we know we have a relative min. So here's that picture. If I'm changing from a negative slope to a positive slope, that means I have a relative min. Here, our second option, if we're changing from positive to negative, that means I'm going to have a relative max. Now the other option is that they won't change signs. If the derivative does not change signs, like here or here, then we don't have a relative min or a relative max. And those we'll talk about later. You want to keep these justifications in mind, these explanations. You're going to use these to justify your free responses, anything about critical numbers. So keep this first derivative test in mind. All right, so let's continue from our first example. Now that we've already identified the intervals of increasing and decreasing, let's classify those critical points. So we already said that we had increasing intervals here and here, and a decreasing here. So now we just need to track the derivative here. It's changing from positive to negative. So I know that my critical number is a max according to our first derivative test. And then from here to here, the derivative is changing from negative to positive. So I know that this critical number is a minimum. So let's start all from scratch in this example. I have my function here, and we're going to try to classify these critical points. So first of all, we've got to find our critical numbers, wherever f prime of x is 0 or does not exist. And you can probably tell right away that this function is going to have a vertical asymptote right here. So we know that it's going to have a vertical asymptote at negative 1/3, which means if we have an asymptote, then our derivative is not going to exist at that asymptote. So that's one of our critical numbers. The other critical numbers we're going to get by actually taking the derivative. So use the quotient rule. You can simplify that a little bit if you want. Set it equal to 0, and here I just multiply both sides by the denominator there. So I was left with my numerator. Simplified my numerator, and then factored it to get my other two critical numbers. All right, so here are my other two critical numbers. I have 3 of them. So if we chart this out, I've got my critical numbers here at negative 2/3, negative 1/3, and 0. All right, and then I've got all my intervals in between on either side. So here, 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 and here. And then we figured out what our derivative value is. So we know our critical numbers were 0 here at negative 2/3 and 0. We got that from here. We know that it does not exist here. We got that from there. And again, we're just using test points to figure out whether it's positive or negative. So for instance, in this interval, I chose -1. I plugged in -1 into my derivative and got a function value that was positive. All right, here we got a function value negative, negative, and positive. So, using our first theorem that we talked about, we can classify our intervals. Our intervals are increasing wherever it's positive, so it's increasing here and here, pardon me, and then decreasing here and here. And then now we can use our first derivative test to classify our critical points. So our derivative changed from positive to negative, so I know I have a max here. Right here in this interval, right here, this critical point, it stayed negative to negative, so I know it's not a min or a max. In fact, we know it's a vertical asymptote there. And then here, the derivative changed from negative to positive, so I know I have a min there. So that's how you find and classify your critical points without having to look at the graph. But let's look at the graph, because I do want you to see why this does have a min and a max. So if you graph this, here's your vertical asymptote at -1/3. But notice that this has a slant asymptote. I don't know if you remember from pre-calc. You can do your long division with your numerator and denominator and get that slant asymptote equation. All right, but here's where we're having our relative max and relative min. All right, so just to give you a good example. Don't forget to try those book problems that are on the board. They're also on my website. I also have the filled in notes on my website as well. So hopefully I will see you guys on Tuesday, and let me know if you have any questions. Thank you, guys.